You need to watch this if you struggle with turning messy raw data into a dataset that's actually ready for modeling. And by the way, all the important resources and links related to everything we discussed today can be found in the description section below, so don't forget to check those out. Welcome back. Today, we're diving even deeper into the journey from raw, chaotic data to a dataset that's truly ready for modeling. Whether you're a seasoned data scientist or just starting out, this process is the backbone of any successful data project. Previously, we tackled the messy world of raw data, cleaning missing values, fixing data types, and removing duplicates. These steps might seem tedious, but they're absolutely essential. Without a clean slate, any insights or predictions we make could be misleading or just plain wrong. We made sure our foundation was solid because a model is only as good as its data. Think of it like building a house. If the foundation is shaky, the whole structure is at risk. In data science, that foundation is your cleaned and organized dataset. Next, we dove into feature engineering, creating new features like turning start date and end date into duration to give our model an edge. This is where creativity meets technical skill, as we invent new ways for our data to tell its story. Feature selection followed. Not every feature helps. We picked only the most impactful ones, trimming away the noise. By focusing on what truly matters, we make our models faster, more accurate, and easier to interpret. Now, our data is clean, enriched, and focused, ready for modeling. It's like having a well-organized toolbox, where every tool is sharp and exactly where you need it. But don't get too comfortable. The next step is critical: preparing our data for honest evaluation. This is where we separate the professionals from the amateurs. This is where true data science skill is tested. It's not just about building a model, but about making sure our results are trustworthy and can stand up to real-world scrutiny. Before training, we must ensure our evaluation is fair and unbiased. If we don't, we risk fooling ourselves with results that look good on paper, but fail in practice. Today, we'll learn how to set up our data for a real test of our model's abilities. We'll talk about splitting data into training and testing sets, and why this matters so much for honest evaluation. Let's get started on this crucial phase. With the right preparation, we'll be ready to build models that don't just perform well, but truly make a difference. The real challenge begins now. Get ready to put your data science skills to the test and take your project to the next level. Here's the golden rule. Never use your test data for training. This rule is non-negotiable. Using test data in training is like a referee betting on the game. If your model sees the test data, it just memorizes answers, giving you a false sense of success. In the real world, such a model will fail on new data. The goal is to build a model that generalizes, not memorizes. Always keep training and testing data separate. This is the foundation of trustworthy AI. Imagine Rohan, a student who's determined to do well in his exams. He spends hours at his desk, poring over his practice book, memorizing every answer word for word. Instead of focusing on understanding the underlying concepts, Rohan is just memorizing solutions, hoping that the same questions will appear on the real test. When he takes a practice test at home, he breezes through it, feeling confident and prepared. But when the actual exam day arrives and the questions are different, Rohan suddenly feels lost and anxious. He realizes he can't apply what he memorized to these new problems. This is exactly what happens with overfitting in machine learning. An overfitted model memorizes the training data so well that it can't handle anything new. It performs perfectly on familiar data, but when faced with new, unseen data, it fails to deliver accurate results. Overfitted models might look impressive during training or rehearsals, but in real-world situations, they often collapse, just like Rohan did during his exam. They lack the flexibility to adapt to new challenges. To prevent this, we use a separate test set. Think of it as a final exam that the model has never seen before. This test set is crucial for checking if the model has truly learned the patterns, or if it's just memorized the answers. By evaluating the model on this unseen data, we can see if it genuinely understands the underlying structure or if it's simply repeating what it's already seen. This step is essential for building models that work in the real world. Honest evaluation with a test set helps us avoid deploying models that are brittle and unreliable. It's a reality check that saves time, resources, and reputation. The test set acts as our safeguard, protecting us from the dangers of overfitting and ensuring our models are truly ready for real-world use. It's the ultimate check to make sure our models can handle unexpected challenges and perform reliably outside the lab. Always keep your test set hidden during training. Never let your model peek at it, just like a student shouldn't see the final exam questions in advance. Only by following this discipline can you truly trust your model's performance and be confident in its predictions. Overfitting is a common trap in machine learning, but with proper testing and careful evaluation, you can avoid it and build models that stand the test of time. That's how we create robust, reliable models that succeed not just in practice, but in the real world. To follow the golden rule in machine learning, we always split our data into two main parts, the training set and the test set. This is a crucial step to ensure that our results are honest and reliable, and that our model can truly generalize to new, unseen data. By dividing our data, we prevent the model from simply memorizing the answers, and instead encourage it to learn real patterns that will hold up in the real world. The training set, which usually makes up about 70 to 80% of the data, is where the model does all its learning. Here, the model studies the data, identifies trends, and tries to understand the underlying relationships. This is the foundation for building a strong, accurate model. The test set, which is typically the remaining 20 to 30%, is kept completely hidden from the model during training. We only use it at the very end to see how well our model performs on data it has never seen before. This helps us get a true measure of its accuracy and prevents us from fooling ourselves with overly optimistic results. In Python, the Scikit-Learn library makes this process incredibly simple with its train-test-split function. This tool is widely used by data scientists and machine learning practitioners around the world. For example, you can use the following code from Scikit-Learn.model selection, import train test split, x train, x test, y train, y test, a train test, split x, y test, size 0.2, random state 42. This single line of code handles the split for you, making your workflow much more efficient. Setting the random state parameter is important because it ensures reproducibility. This means that every time you run your code, you'll get the same split, which is essential for consistent results and for sharing your work with others. The train test split function shuffles and divides your data, giving you 4 separate sets: x-train and x-test for your features, and y-train and y-test for your labels. This clear separation helps keep your workflow organized and your results trustworthy. This split is absolutely essential for fair, unbiased model evaluation. It ensures that your model is tested on data it has never seen, just like it would be in the real world, so you can trust the results. Remember, never peek at the test set during training. If you do, you risk contaminating your results and making your model seem better than it really is. Repeatable experiments are the backbone of good science. By keeping your data split and your process transparent, you make your work more credible and easier for others to verify. With our data properly divided and our process set up for fairness and reproducibility, we're now ready to move on and choose the best model for our problem. With our data split, it's time to pick a model. First, identify your problem, regression or classification. Regression predicts continuous values like house prices or sales numbers. Classification predicts categories like spam versus not spam or yes versus no. For example, predicting if a customer will buy a product is a binary classification problem. Regression models include linear regression. Classification models include logistic regression and naive Bayes. Today, we'll focus on classification. Our goal: predict if a customer will buy, based on features like age and income. This is a classic yes-no scenario, perfect for classification. Let's choose a simple, effective classifier to start. For classification, logistic regression is a fantastic starting point. Despite its name, it's a classification algorithm, fast, interpretable, and efficient. It predicts the probability of a data point belonging to a class. For example, it might say, there's an 85% chance this customer will buy. Logistic regression uses a sigmoid function to squash outputs between 0 and 1. If the probability is above 0.5, it predicts yes. Otherwise, no. It's easy to understand how each feature affects the prediction. This transparency is valuable for stakeholders. Logistic regression sets a strong baseline for future, more complex models. Let's see how to implement it. To use logistic regression in Python, import it from Scikit-Learn from Scikit-Learn.linear model, import logistic regression. Think of this as grabbing the recipe for our model. Next, create an instance model, on logistic regression. This gives us a fresh, untrained model, like hiring a new intern. You can customize it with parameters, but defaults work well to start. This process is the same for any Scikit-Learn model. Consistency makes experimenting easy. Our model is now ready to learn. The next step, training. Let's teach our model using our training data. Our model is a blank slate. It needs to learn from data. In Scikit-Learn, training is simple model.fit, x train, y train. This is like giving our intern a manual and answer key to study. The model analyzes patterns, adjusting its internal weights to best map features to outcomes. This process can be computationally intense, but Scikit-Learn handles it efficiently. Once fit finishes, our model is trained, no longer an intern, but an expert. The fit method is universal across Scikit-Learn models. Now our model holds the knowledge from the training data. It's ready for the real test unseen data. Let's see how it performs. We've covered the essentials, the golden rule splitting data, choosing classification and training with logistic regression. Our model is now trained and ready, but how well does it really perform? The true test is making predictions on the unseen test set. Next, we'll evaluate our model's performance using metrics like accuracy, confusion, matrix precision, and recall. This is where we find out if our model truly understands the data or just memorized it. Stay tuned for the next step in our machine learning journey. The final exam awaits.